All right, so this week we have five, hopefully simpler problems. So I'm going to go through them one at a time and show you my solutions and so on. Okay, so the first one, alphabet spam. You're given some text, one line of string with a string consists of at most 100,000 characters, and you have to figure out the ratios between white space, lowercase, uppercase, and symbols. And symbols are basically any characters that doesn't fall into one of these three groups. So really the main question is, how do you identify these three types of characters and keeping track of the count and computer ratios at the end. And also they tell you that there are actually no white spaces, but white spaces are actually underscores. So you have to check underscores instead of spaces. And that actually makes it easier because if you just read an entire string, you don't have to worry about blank spaces breaking up your string when you read it. It will just read it in one go. You count it all, and then the ratios of white space, lowercase, uppercase, and symbols in that order. So you figure out the total number of characters, and then divide each of the counts into that total. And that's basically all you have to do. So let's just look at how I do this. Because I have four numbers, I'm going to use a count of four things. And I'm just going to remember that space is the first one, lowercase, and then uppercase and symbols, because that's the order that I have to print things in. I can read this as one string because I don't have to worry about spaces. And then I just loop through the entire string. So this is a way to loop through the characters in the string using the C++ range-based for loop. So for all the characters in the string, if it's an underscore, then I increment the space by 1. If it's lowercase, so this is lower is a function in C++ that checks if a character is a lowercase. You increment lowercase count. If it's uppercase, you increment the uppercase count. Otherwise, it must be the symbols count. And then at the end, I just go through the four counts, and for each one, print it out. And I print it out with 10 decimal places. So this is, remember that when you divide an integer by another integer, you need to cast at least one of them to double if you want a floating point answer. And it says that your answer should have an absolute or relative error of at most 10 to the minus 6. What does that mean? An absolute error means that it has to be correct up to 6 decimal places. And then relative error basically means that it has to be correct up to 6 significant digits. So what's the difference between the two? So if you have a number that's really small, if the answer is like, I don't know, 1, 2, 3, 4 times 10 to the minus 10, then if it's just for absolute error of at most 10 to the minus 6, then 0 would be the correct answer because 0, it's close to the right answer if the answer is very small. Relative error means that you are actually correct up to 6 significant digits, regardless of how big or how small it is. Actually, the problem is that it's more useful. This relative error is more useful when the correct answer is something really big. So if you have something like a billion, right? And then, well, it's really hard to get absolute errors to be 10 to the minus 6 when the number is really big because it means that you have many, many digits of accuracy. When you have many digits of, let's say you have 8 digits of accuracy and the answer is a billion, you would use it all up in the integer part. You wouldn't even get to the decimal part. But relative error just counts a number of significant digits. It means that only the first 6 digits, 7 digits have to be right. Okay, so for an answer, that's supposed to be between 0 and 1. Probably doesn't really matter whether you use absolute or relative error. Okay, so that's the first question. I'm gonna go skip over the second one for now and look at this mult. So I'm not going to go through too much of the problem statement, but I'll just kind of explain what you're supposed to do. So the first line of input contains an integer n, which is the number of integers to follow. So 10. Then you start, the next number is the divisor that you're looking for. So 8. And then you keep reading these numbers until you find a number that's divisible by 8. So 24, and now you print 24. Immediately after that, the next number will once again be the number that the divisor that you're looking for, and you read again until it's divisible by 14. And then the next one will be the divisor you're looking for, and then you're done because there's no more numbers. So really, it's just a matter of making sure that you are in sync with what is the divisor that you're using right now, and what number where it is divisible by the divisor you're looking for. So let me go to mode. And the program is really straightforward. You have the first number, which is n. Okay, it's the number of numbers to follow, and I have a loop here that loops through n times and reading the next number all the time. And I am going to use this first, which is a divisor that I'm looking for, and initialize it to be -1. Every time I see it -1, it means that I don't have a divisor. So the next number to come, it's going to be the next divisor. You can use other ways to remember this, but that's how I did it. I know that I can use -1 because it says that all numbers in the sequence are positive integers. So I know that -1, it's never the correct the correct divisor that I'm looking for. All right, so if the divisor I'm looking for, it's less than 0, that means that the next one, the number that I read, needs to be put in the divisor. Otherwise, I already have my divisor, and you just ask, is the number I just read divisible by the divisor? If so, print it out and reset the divisor. So the next time I read the next number, it will be the divisor. There are other ways you can do this, I guess, with the way you control this structure, this loop, but that's the way I choose to do it. You could also, instead of having this as a one single for loop, you can have double loop. You can read here the next divisor, and then you can have a while loop, right? That reads until it's divisible. The advantage is that it makes it easier to keep track of the divisor and the rest of the loop. The disadvantage is that you need to somehow know, well, even whichever loop you're in, whether it's the inner loop or outer loop, you need to check constantly whether you have finished reading the 10 numbers or the n numbers and break out as appropriate, and don't try to read more numbers than you have. So either way, I guess you can do it either way. Whether you do one single loop or double loop, it's the same kind of idea. Both have the advantages and disadvantages. Okay, so this one is not too bad. Okay, now let's look at the basketball one. So Alice and Barbara are playing some friendly basketball games, and you agree to keep rules. Each successful shot earns them either 1 or 2 points. First player to 11 points wins, with one exception. If the score is 10-10, the previous rule is replaced by a win by 2 rule. The first player to lead the other by at least 2 points wins. So basically, you're going to have to do a couple of things. First, you have to keep track of how many points each person has. Then you have to figure out if you're in the first part of the game or the second part of the game. Second part of the game means that the score has tied 10-10. And then, depending on whether you're first part or second part, then of course you determine whether somebody has won a game or not. Okay, so basically you have a bunch of characters, A or B, alternating with either 1 or 2. So you have to basically read the sequence of pairs. And then you have to say who won. Okay. So what I'm going to do is I'm going to use an array of 2 numbers to keep track of the 2 scores, A and B. A would be 0, B would be 1. And I use the string here to indicate, just so that I know who is, which one is 0 and which one is 1. Okay. And then I have this Boolean variable that keeps track of whether I am in the tie-breaking situation. So tie-break is false. That means I'm still in the first part. I haven't hit 10-10. If tie-break is true, then I have the 10-10 tie. I read it as a string, and then I just basically loop through it 2 characters at a time. Okay, so the first thing I do, I figure out who it is. If it's A, I convert it to 0. If it's B, I convert it to 1. And then the second character, it's the number of points. So I remember I take it apart, and then I update the score. So now that I have the score, I basically have to decide, do I have a winner? How do I have a winner? If somebody has 11 points and I have not reached the tie break, so that means the first rule, the first player to win, the first player to 11 points win, that's the first rule. So, and I only have to check the person that I just incremented. I don't have to check the person that, I don't have to check the other person because, why? Because if I have been keeping track of the score correctly so far, the other person hasn't won, and the other person cannot win because the other person hasn't scored. Okay, so I only have to check the person that just scored. If it's not tie-breaking and that person got at least 11 points, that person won. Or if it's a tie-break and the person that just scored minus the other person, it's at least 2 points. So you win, you lead the other by at least 2 points. And the other person, because the numbers that I use to indicate the players are 0 and 1, 1 minus 0 is the other person. 1 minus the first player is the other person. So in either case, either you win by the first rule or you win by the second rule. If you win, you print out the name of the person that won, whether it's A or B, and then you just quit the loop. That's it. You're done. If nobody has won, then you have to keep going. But before we keep going, we check if both of these people have exactly 10 points, then now you have to remember that we're in the second stage. So we have to remember tiebreak is true. And that's it. Okay, so basically that, as I said, there are 2 parts to this. You keep track of the scores of each person, and then you keep track of whether you're tie breaking or not, and then you apply the correct rule. Now you could, if you want, have the more, I guess I should say, less complicated statement. You can say if tie break, then you check this. If not tie, else you check. Sorry, if tie break. So if not tie break, you check this. Else you check this. But the way I wrote it here, I basically combine both conditions and just say this is the winning condition, either rule 1 or rule 2. You can write it either way. All right. Let's look at field trip. Field trip, you have 3 buses of equal capacity, and you want to split the groups, split the classes into 3 sections, so that each bus will be completely full. And you have to figure out if it's possible where do you want to break it up? Now, if you read this problem carefully, at no point did they tell you how big the bus is. Okay, so that the bus is actually kind of indeterminate. You have to kind of figure that out, I guess. But you do have to, so if this class sizes, let's call it C1, C2, C3, C4. If these are the class sizes I give you, you must board the first bus in this order. So bus number 1, you must board C1 up to C4, and then everybody else must go to the next group must go to bus 2, and then the last group must go to bus 3. You're not allowed to reorder them. Okay, and if you read the problem carefully, basically they say that if 3 buses have unequal number of students, then some bus will have to have teachers. So the whole question, if you do a little bit of reading comprehension, is to ask, can you take these classes and split it into 3 groups of equal size? That's really all there is to it. But they don't tell you what is the size. Well, if they have to be equal, then basically what you do is you say total. The total is the sum of all the CIs. So add up all the people in each class. And you want to be able to, for each bus, the target number of people should be exactly the same as total divided by 3. So right off the bat, if this is not an integer, so this has to be an integer, but if this is not an integer, there's no way you can do it. Okay, so that's the first part. The second part is, well, how do you separate the groups? Is, how do you do it if you have a chance? If the target is, I don't know, 99, then so if the total is 99, then the target would be 33. So you have a chance, but it's not guaranteed, right? Because you could have something like 11, 22, and 66 as your 3 classes, and there's no way you can split them. But if total is not divisible by 3, then you got no chance. Okay, so what are we going to do? What we're going to do is we basically just start adding these numbers, right? C1, C2, and we just scan this way. And we keep adding this number, and when we see, if we ever see something, the total exactly the target, then we know this is where we cut. If you see the target, if you see the total being bigger than the target, maybe you get 34, but you have never seen 33 before because maybe the previous one you see is 31, then you know that you cannot do it. So that's all you have to do. You go through, you see until you either get 33 or bigger. If you see something bigger, you know you can't do it. If you see exactly 33, that's where you cut. And then you scan again, looking for another 33, or if you want to don't reset the counter, I guess you can just look for 66. Again, if you see something that's bigger than 66, you know you cannot do it. And then if you can do the first 2 groups and the third group is guaranteed, because that's whatever's left over. So this is basically what we're going to do. And you can write it this way. But the way that I wrote it is a bit different in my code. So what's the difference is that I use a couple of STL algorithms, not necessarily that it's any faster to run, but it's faster for me to write. So I'll just, let's say this is my class size. I don't know, 2, 4, 1, 3, 7, 5. I'm just making numbers up. One of the things that you can do, it's what is called partial sum. Partial sum basically computes an array where each entry is the sum of the first array. So if you want to compute a partial sum of the first array, It's the sum of everything up to that point. So you see here, the next entry is 28 because the sum of everything up to here is 28. There are many different applications of partial sums, but we'll just look at this one right now. So this will be like this. And so what I'm going to do, right, if I'm just doing the algorithm we talked about before and scanning and adding up the numbers looking for 33 or whatever, that's essentially the same as computing in partial sum first and then searching in this array for 33 and 66. In this case, of course, the numbers don't work for 33 and 66, but that's the idea. And because we can use linear search, which in SQL is fine, that means I can do the whole thing without actually writing a single loop, apart from maybe reading the input. Is it any better than the way that you write your own loop? Not really, in terms of runtime. But in terms of, making it easier to debug, making it easier to write code that's correct and so on, it's easier to think about, easier to write, so it saves programming time. Okay, and the other thing that to make sure, actually, is to look at the size. You have up to 1 million classes, and each class section can be up to 10,000. So 1 million is 10 to the 6, 10,000 is 10 to the 4, so that's 10 to the 10, which is just enough for a normal integer. So 10 to the 10, no, wait, 10 to the 10 is 10 billion. So actually that's too big. You need long, I think, because 2 billion and change is about the size of a 32-bit integers. Hang on, I used integers. Why did I use integers? Let me just make sure. So this is 10 to the 6, this is 10 to the 4. And to the 6 is 1 million. Each class can be at most 10,000. It's this much, 2 to the 31 minus 1. Yeah, okay, it's too big. So why did I guess, oops, I should not use integers. I should use long, but somehow there's no test cases that test that. So, okay, so let's change all of them. Now this can be integer. And then partial sum. Actually, partial sum can be long. So let me just make everything long. Okay, so I compute partial sum and I put the answer back into the class sections. And then I find whether I can find targets and 2 times target. And I, for some reason, never checked if, oh yeah, here it is. If it's not divisible by 3, I print -1. And then I basically will return an iterator to the position where it's found. So an iterator is not an index. I have to subtract the beginning, and that will tell me the index. And I have to add 1 because in this problem, things start at 1 instead of 0. Okay, so actually, yeah. Okay, so let me reiterate. You need to use long, even though this problem, for some reason, if I use the int, it doesn't seem to catch me. Okay, that was my bad. But basically, that's how I did it. So notice that except for this input, I don't even have a loop. I just make use of the STL functions, partial sum and linear search. to help me get through everything. Okay, the last problem that I want to talk about, Ocean NT11. He wants to count, okay, the 100 test cases. Each case is an n. N is the length of the strings, and you want to count how many binary strings there are of length n that do not contain 11 as a substring. So you can have as many zeros as you want, but once you have a 1, the next digit must be 0. And then the numbers can be quite large, so you want to output the answer mod this. Okay, so basically, let's compute it without worrying about the mod. And then we will just mod everywhere. If you want the answer at the very end to be correct, mod something, you can actually just mod the answer, this thing every single step of the calculation, and you'll be fine. Okay, so let's think about this kind of thing. This is a counting problem. And so f of n is the number of binary strings without 1 that's a substring. Oh, number of binary strings of length n, of course. All right. So usually with counting, you want to start small and just try it out. What is the smallest n you can have? 0. How many empty strings are there? Oh, just one string, one empty string. So you have to ask, what is quite often the question of F0 is a little bit weird because, what is an empty? Is there a string that's empty? And the answer is yes. An empty string certainly does not have 1 as a substring. Now the questions that they give you, actually, they will not ask you n equal to 0, so perhaps we don't care. All right, f of 1, how many binary strings of length 1? Well, both of them, both 0 and 1, are good strings because neither of them have the substrings 1, 1. You only have length 1, you can't have this substring. F of 2, well, you have 0, 0, 0, 1, 1, 0, 1, 1. There are four strings, but we cannot count this one. So that's 3. F of 3, so again, you can try them all. So at the beginning, when you don't know what to do, try the small cases because you can often just list them all. And then you cross this one out because it says 11. This one has 11, this one has 11, and you see this 5. And if you want, you can do f of 4, f of 5, and so on. But eventually you don't want to do this anymore because, well, why? Because it's going to be too much. But if you were to do f of 4, you will probably see, if you didn't make any mistake, it's 8. And at this point, as a computer science student, hopefully you'll see some kind of pattern because this is a famous sequence called the Fibonacci numbers, right? Every number is the sum of the previous 2. But, you don't really want to base your proof, if you want to call it that, by first 5 numbers. Maybe it doesn't work out, the 6th number or whatever. So you need to have a reasoning. This is a suspicion, and you have to ask yourself, does it actually make sense? Okay, so somehow we're guessing that f of n is the same thing as f of n plus f of n minus 2. F of n minus 1 plus f of n minus 2. The sum of the previous 2. Why? Okay, now let's think about it this way. You want to count how many strings there are with n symbols, n zeros and ones, and that no 1 ones anywhere. So if you think about this, there are n symbols. If there are n symbols, the first question that you might ask, one of the questions you might ask is, well, what is the first symbol or what is the last symbol? Okay, and we just look at either first one or the last one, doesn't matter. Okay, let's just look at the first one. What can this be? It's either 0 or it's a 1 followed by n minus 1 thing. Okay, and those are the only two choices. So if we know how many strings of length n starts with 0 and how many strings of length n starts with 1, then all we have to do is add them together, because these are the only two choices and they do not overlap. There cannot be strings that are counted by both, because a string, it's either starting by 0 and 1 or 1, not both. So now we ask, let's look at the strings that start with a 0. What can go in here? Can it start with 0? Can we start with 1? Can we do anything? And the answer is you can actually do anything you want as long as you don't have 1, 1 anywhere. Why? Because if you have any strings you want, as long as you don't have 1, 1 anywhere, adding a 0 to the front cannot introduce the offending 1, 1. So whatever strings you have, as long as it doesn't have 1, 1 in there, adding 0 would work. And similarly, and I guess conversely, if you have a string that already has 1, 1 in there, adding a 0 would all still make it unusable. So there's no way you can start with a bad string of n minus 1, add a 0 to the front, and all of a sudden it becomes good. So basically all the strings, legal strings that are length n minus 1, if you add a 0 in front, that's a string of length n that works. And that's this component. These are the number of strings, f of n minus 1 are the number of strings of length n that starts with 0. What about this? If you start with a 1, then you are forced, the next symbol must be 0. There is no other way. You're not allowed to put a 1. Right? Because as soon as you put a 1, you have the illegal 1, 1. So that's not possible. So as soon as you start with a 1, you must follow with a 0. And now that you know that the first part starts at 1 and 0, then we use the same reasoning and say that the remaining n minus 2 characters can be anything as long as 1, 1 is not there. And that's the f of n minus 2. And that's why this is actually Fibonacci numbers. Now, it's not really that important that this is Fibonacci numbers. The important thing is to recognize that when you're doing counting kind of problems, it's often the case that you want to start small, try a few small cases because you can count them all, see if you see a pattern, but it doesn't even matter if you don't see the pattern. And then you try to figure out, for the general case, if I just look at, let's say, the first character, the last character, you're making the first choice or the last choice, how many ways can you do it? Well, in this case, there are only 2 ways. So break it up into the 2 cases, and then you try to reduce the problem into something smaller recursively. And in this case, we discovered it as just the sum of the previous 2. In other cases, it might be a little bit more challenging. But the point is, you want to look at these problems by breaking down the problem by sort of eliminating the choice on the first step or the last step. So let's just very quickly see my solution. So here it is. In fact, compute all possible answers at the beginning, because there are only 10,000 things that they can ask you. They can ask up to 10,000, up to the 10,001. I remember the mod, which is 10 to the 9 plus 7. Read a number of cases, and then I just compute. So I initialize the first two, and then everyone is the sum of the previous two, and don't forget to mod it. And that's it. Go through the number of cases, read in the question they ask you, just look up the table, and that's the answer. Okay, so this set, hopefully that it's not too hard, but still there are a few things that you can learn from it, I hope. And then next week I will have more problems. All right, see you later.